Yeah. Good evening. So what we discussed in the last class, tell me? Lewis dot structure and octet rule, and then next Fazan's rules, like we discussed ionic bond and covalent bonds and factors affecting ionic bond. The next, when we are discussing about covalent bond, we discussed also the Fazan's rule that explains the covalent nature in ionic compounds. For example, NaCl, KCl I have given, which is having more covalent nature. Both are ionic compounds, but covalent nature is more in which case? KCl or NaCl? So covalent nature, that small size cation, big size anion. So KCl, NaCl, Cl, Cl are same here, anions are same, but cation size you can consider here. K plus Na plus, which is smaller? Na plus is smaller. Okay, so Na plus is smaller means that makes it to be more covalent. Okay, therefore more covalent compound has lower solubility, means as covalent nature increases in ionic compound, its solubility decreases, as well as its melting point also decreases. Remember this point. Okay, and after that what we discussed? Yeah, we have almost entered into this thing, valency bond theory. Okay, so now valency bond theory here, so it is given by Pauling. So what he says here, the bond between two atoms, as per him the bond between two atoms is covalent bond. What type of bond it is? Covalent bond. So how this covalent bond is formed? See, look at here. So according to this theory, a covalent bond is formed between two atoms by overlap of half-filled valence electron or half-filled valency atomic orbitals of each atom. For example, here I am saying hydrogen atom I have. Okay, in order to explain hydrogen molecule formation, I have two hydrogen atoms. Okay, 1s1 and 1s1. Right now, so this is 1s orbital of this hydrogen atom and this is 1s orbital of the other hydrogen atom. Okay, having 1 electron in each of them. Okay, so these orbitals will overlap. Okay, there is a concept called overlap now. Okay, so what do we mean by overlapping? The partial interpenetration of these two atomic orbitals. What do we mean by partial interpenetration? Interpenetration I am saying, it means this will penetrate into this orbital or this will be penetrate into this orbital. So it means they will merge each other, something like this. Like this. Okay, so now here this is the nucleus of this atom and this is the nucleus of the other atom. Okay, so now the electron, here 1 electron and here 1 electron are there now, so that will be present here in between like this. Okay, then these two electrons are shared between the nucleus, two nucleus of the two atoms. So therefore it is making, this electron pair is making a bond between two hydrogen atoms like this. Okay, so now if we want to get more clarity on this, just look at this graph. Here we have two hydrogen atoms. This red color bars represents two hydrogen atoms, which are very far from each other. Okay, yeah, Abdul Rahman, good evening. Yeah, which are far from each other right now. So as we bring them close to each other, what happens? See, this is the two orbitals which are very far from each other. So this is the internuclear axis. This is the internuclear axis which I am taking on x-axis, and this is the energy. See, as we move them close to each other, what happens as we move them close to each other? See, as internuclear distance is decreasing if we come this side. So as we come this side, what about their energy? Energy is getting decreased. So lower energy means more stability it has. Okay, so now we are reaching a point. See, we are reaching a point as we move this side, we are reaching a point here. This is the internuclear distance where there is a minimum energy found when two hydrogen atoms are placed together. Okay, so this is the minimum, this is the distance. This is the internuclear distance where we are finding minimum energy. Minimum energy means maximum stability. Okay, so the two hydrogen atoms when placed with this distance 74 picometers, they are having maximum stability, which is explained by looking at its minimum energy level. Okay, now if I further move them closer, what happens? No, see, you need to understand it like this. This is the nucleus of one atom and this is the nucleus of other atom. Okay, so now we also have one electron here and one electron here now. So what is the charge of electron? Negative, right now. So now between two like charges, what we have? Repulsion. Between these positive charges also we have repulsions, but between two negative charges, like opposite charges, attractions will be there. So now if forces of attractions are dominating, then that makes it to be more stable. If forces of repulsions are dominating, that makes unstable. Okay, so now if I cross this minimum, this distance, what happens? Repulsions are dominating. It means, see, this is the nucleus and this is the nucleus. If we brought them very close, what happens between these two same charges, like charges, repulsions are dominates right now. So after crossing this distance, this 74 picometers, its energy is getting raised. See here, why it is getting raised? Because repulsions are dominating. Okay, so it means this is the minimum distance that you can put them together. Okay, and where they have force of attractions dominating than the repulsions. Therefore, that distance is called as internuclear distance or the bond length. So in hydrogen molecule, we are writing like this in a hydrogen molecule. What is the bond length we have? What is the bond length we have? 74 picometers. Remember this. Okay, if I move it to 70 picometers, what happens? Repulsions will dominate. Now this side if you move, repulsions will dominate. That is what energy is increasing here. Okay, so that's what the minimum energy will be absorbed at the 74 picometer that we are considering as the bond length of this molecule, hydrogen. Is that clear?
74 picometers, the radius of the molecule?
Yeah, radius in the molecule.
The atomic radius of
no,
hydrogen?
that is a bond length, not radius. Bond length it is, complete distance, like full length, bond length. Okay, right. Now what we discussed, the partial interpenetration of atomic orbitals are called overlapping of those atomic orbitals. Like I have shown you, the two atoms orbitals are merging to some extent. That is what the partial interpenetration means. Okay, so now if we refer to the minimum energy state, the formation of hydrogen, so that is enough near as to have their atomic orbitals with a minimum energy, which are called as partial interpretation of atomic orbitals. See here, this is a distance. This is the distance. See, if you consider 1s orbital of hydrogen atom, 1s orbital, see they entered, this is entered into this and this orbital also entered into the other atom. So we can say like two orbitals here. So that is what the partial interpenetration means. Yeah. So now this overlapping is of different types. So we have the overlapping between two atomic orbitals can be a positive overlap, negative overlap or a zero overlap. So what do we mean by positive, negative and zero overlap? Let's understand it better by looking at this thing. See here I have this pictorial representation. See, we not only have s orbital, we also have p, d, f orbitals right now. Yeah. So now look at here. I am taking, we have p orbital with shape something like dumbbell shapes, like this right now, dumbbell shape. So we have p like x axis, y axis, z axis, right? So it means we have px, py and pz. Right now, so let us say I am taking something along this px axis or pz axis, whatever you want to take. So let us say this is z axis and this is x axis I am saying. So this is along the z axis I am saying. See, this orbital has two signs, one is positive I am keeping, one is negative. Something like if you take a wave, so how this wave will be, one is positive lobe, another negative lobe. Similar to that you consider positive and negative lobe. Now I am taking, see, in order to form a molecule, the orbital of this atom and orbital of the other atom should overlap. Right now, it means two orbitals are required, two atomic orbitals are required. So this is one atomic orbital of one atom and another atomic orbital of another atom will also be there now. Like other atoms atomic orbital also will be there. Okay. So now that is also can have positive and negative sign for the p orbital. Right now. So now if the positive overlapping is taking place, like same side, whether it is positive or negative, what I am saying, that should be of same side. Then that resulting overlapping is called positive or in phase overlap. What I am saying, same sign overlapping should be takes place, that will be considered as in phase overlapping or positive overlapping. Okay, so now other possibility is what? One can be positive and the other orbital can be negative. Opposite sign overlapping can also be taking place now. Something like, see here, so one orbital is having positive sign, other orbital is having negative sign. So this makes it to have negative overlapping or out of phase overlapping. So two types, one is in phase, other one is out of phase. So in phase will be when both signs are of same. Orbitals which are undergoing overlapping having both signs, or both sign same sign overlapping gives us positive or in phase. Opposite sign gives negative. Out of phase or negative. Is that clear? Right. Okay. So now for understanding, let us say here I have, first of all we will see sigma bond. So tell me in which case and what type of overlapping is taking place here? In the first case and second case, tell me.
First case positive, second case negative.
In first case, see, these are of same sign lobes now. So that gives us a positive overlap and resultant will be having this kind of amplitude. Okay, so now the negative sign here and negative sign here and positive sign in between. Okay, in the next case, see, these are having opposite signs, so means it gives us negative overlapping, right now? Something like this. See, we got a nodal plane here. What is mean by node? I told you in the previous classes, atomic structure we discussed now. What is that node? Probability of finding electron is 0. So this is the nodal plane we have got here, where probability of finding electron is 0 in this case. But in this case amplitude got increased. It means probability of finding electron is more in this case. It means the positive overlapping will gives you sigma bond formation, sigma bonding. What it gives? Sigma bonding. See, those are like this now, head-on overlapping is taking place, that gives us sigma bonding. And this one, see, these are having opposite now, so this gives you sigma anti-bonding. Okay, anti-bonding I am writing with sigma star. So we got one bonding, another one is anti-bonding. Okay, you can write BMO, ABMO or AB, you can just put it. Okay, right. Next here, see, this is what the sigma bond formation representation. Similar to this, we can also have pi bond formation now. So pi bond will be formed. See, how many p orbitals I told you? Px, py, pz. Out of that, one of the orbital, let us consider z is the internuclear axis. Those are going to form a sigma bond, and two other are perpendicular to z axis now, like p. That two pi bonds will be formed from those two perpendicular orbitals. Like, what are the two perpendicular? One is z axis, z is over here, pz is over. Next we have py and py and px. Okay, so positive, negative. So now what type of overlapping can take place? Tell me. This is head-on overlap, this is sidewise overlap, like parallel overlap, like this come each other. Okay, so now this overlap will gives us what? See, if this is the internuclear axis, so we can have something like this. See, so this is positive sign, negative sign here. Okay, so this is bonding only now, so you should call this as pi bonding. Okay, what type of bonding it is? Pi bonding or pi bond formation takes place with this parallel overlapping or sidewise overlapping. Now, how this pi anti-bonding will be formed? Tell me. One should be positive and this should be having some negative sign here and positive sign here. Okay, see, opposite signs now. So it will be having now something like this. If you want, you can take it in this manner. Like this you can consider. Okay, so look at here, what is the sign here? I should write positive, and here negative, negative and positive. So will they overlap? No, not overlap, they won't overlap now. So that's what I have written in the opposite manner. So now here see how many nodal planes are formed here. One nodal plane and one more nodal plane here. So how many nodal planes are formed? In case of pi star, means pi anti-bonding case, we have two nodal planes. Okay, remember this point also. Okay, they will ask, so how many nodal planes are formed in case of pi anti-bonding or sigma anti-bonding overlapping? Okay, is this clear or not here? Right. Okay, next, what is the third case we have? Out phase overlapping. See, this out phase overlapping or out of phase overlapping, I mean zero overlapping we have. So what do we mean by zero overlapping? See, one orbital is something like along this like I am saying y axis, along y axis, and another one is along some z axis. Will they overlap? No, no, right? See, this is a nucleus where we have, see, this will be combined overlap here. Is that overlapping is possible? No. So if we are taking the orbital with improper orientation, no overlapping will takes place. So we can say that case as zero overlapping. Something like, see, this is pz and this is s orbital. Is that overlapping takes place? No. If we take this orbital as something like this and s orbital like this, then we can have a overlapping. sp type of overlapping is possible. Sigma bond formation takes place. But here, not possible. So this is what we are saying it as zero overlapping. See, if I take px and py, they are perpendicular now, like this. Is that overlapping is possible? No. So this is also leads to zero overlapping. Three things are clear now: positive, negative, zero. Okay, right.
So the same like anti-bonding only.
Yes, yes. So even same concept, almost same thing will be studied in the case of molecular orbital theory, like bond form, like sigma bond formation, pi bond formation, how that orbitals are overlapping. Okay, right. Okay, here itself I am adding that concept also, just to make it more clear in again. Okay, so look at here. What type of bonds we have now? Sigma bond. When sigma head-on overlapping is taking place, what I told you, sigma bond formation is taking place. Okay, and next one, when sidewise is overlapping, will give pi bond. So two types of bonds are there, but out of these two, which bond is having more strength? Sigma bond or pi bond? See, when this head-on overlapping, sigma bond formation is taking place, this head-on overlapping will be very effective. That makes it to be more strength. So sigma bond have more strength, or sigma bond is more stronger than a pi bond. Sigma bond is stronger than pi bond. Now I am not saying single bond and double bond. What I am saying, sigma bond and pi bond. So when I say single bond, double bond, you should say double bond is more strong. Why? Because two bonds are there now. One is sigma, again one is pi. This is only sigma. So when two together are there, they are more stronger. So sigma bond is stronger than a pi bond. You can remember. Why? Because what? What is the reason? Due to head-on overlapping. That's it. Okay. Next. So what type of overlappings we have seen? SS orbital overlap like this. Okay. And next, I told you all these things. S and p orbital gives sp orbital overlap like this, but this should be in the proper orientation. Okay. Next, pp overlapping. This kind of overlapping will form what type of bond? Head-on overlapping means what? What type of bond it is? Sigma bond. Okay. And sidewise overlapping will gives us pi bond formation like this. Okay. If they have same sign, I can say additive overlapping gives pi bonding. Okay. If they have subtractive or means with opposite signs, negative overlapping. Okay. That is what we have studied. So basically strength of bond depends upon extent of overlapping. More is the extent of overlapping, more is the stability. So more extent of overlapping takes place in pi bond or sigma bond?
Sigma bond.
That's what. Sigma bond is stronger than pi bond. That's it. Next. We have now concept of hybridization. So what is the use of this hybridization concept? Tell me. Yes, tell me, what is the use of this hybridization? actually we have something like methane and ammonia, this kind of molecules are there right now, right. So for this, what exactly the structure, what is the geometry, how can we explain? Like for example, I am saying methane is having tetrahedral geometry right now, and this is having something like pyramidal shape. So how can we give these structures? So in order to explain this, we have a concept called hybridization. This is a theoretical concept to explain the geometry and structures of these molecules like methane and some other compounds. Okay. So now in order to explain the characteristics of geometrical shapes of polyatomic molecules like ammonia, methane, water, etc., we have a concept called hybridization. This was introduced by Linus Pauling. Okay. So this is what I am saying, this is a theoretical concept, there is no practical or experimental data, they just looking at the other data, they just given this hybridization. Yeah. Okay. So now see, according to him, what he is saying, atomic orbitals combine to form new set of equivalent orbitals known as hybrid orbitals. For example, what is this atomic orbitals? Look at here. When I am saying methane molecule, what is the central atom here we have? What is the central atom here we have? Carbon, right now. So carbon hybrid like atomic number is 6. So what you should write is atomic orbitals are 1s2, 2s2, 2p, 2 we are writing right now. So now represent their orbitals, atomic orbital like 2s and this is 2p, p orbitals are 3 right now. So now what I am saying, during the hybridization only valency orbitals of that central atom will participate. What are the valency orbitals? Only 2s and 2p2. Okay, how many electrons are there here? 1, 2, 3, 4. 4 electrons are there. So now these valency orbitals will combine with themselves and form a new set of orbitals called hybrid orbitals. What I am saying? Hybrid orbital. So what is the use of forming hybrid orbital?
More number of bonds.
Not only that statement. See, tell me between 2s and 2p, what is the energy difference? Which is larger? Which is having more energy? 2p is having more energy. Now again, if I say atomic orbitals, one will be along the x-axis, other will be along the y-axis, other will be along the z-axis. It means what is their angle between the two orbitals? 90 degrees. Right now, px, py, pz means 90 degrees. So now if they combine, we are going to get bonds along the xyz 90 degrees angle. That is not the perfect angle to be considered in the methane. It is having something like 109.5 degrees. The experimental bond angle found to be 109.5 degrees. So how it is forming here? So these atomic orbitals will combine. This whatever the atomic orbitals, the valence orbitals are there now, they will combine and they will redistribute their energies. Now they have different energies. Now they will redistribute their energies, so that what we are going to get when they are redistributing their energies. So 3 plus 1. So 4 orbitals are there now. So they will redistribute energy, means they will get a new set of orbitals with a same energy. Now how many we have? 4 orbitals with the same energy and same shape and same angle between all of them. Okay. So now previously we have 90 degrees angle. Now the 4 are merged and we are getting a new set of orbitals. We should call them as hybrid orbitals. Previously what we called this as atomic orbitals. Now what I am saying? Hybrid orbitals. So these hybrid orbitals are, how many are there? 4 are there now. How they are formed? 1 is from s and 3 are p. So how many hybrid orbitals? Total 4. So what is the name of those hybrid orbitals? sp3. So you should call them as sp3 hybrid orbitals. Okay. Now they will ask, how many s orbitals are there in these? You should not say like that. All of them. What is the name of this orbital? You should say. You should not say it as s orbital anymore. What is the name? It should be sp3 hybrid orbital. So like this, how many are there? 4. When I say atomic orbitals, you can say this is s orbital. But when we say hybrid orbitals, you should say only sp3, not as s orbital. Okay? Because they lost their identity. Now they got a new identity as sp3.
Sir, but they give character also, like 25%.
Character is there, but that is percentage right now. So that is not pure s orbital now. Okay, so now how many electrons we have in the valency? 4 right now. So following the Hund's rule, we should give 1 electron, right? Yeah, we got 4 electrons each of them. Now how many surrounding atoms are there? 4. Each hydrogen atom, how many valence electrons are there? 1 right now. So each of that 1s orbital of hydrogen will pair up with this. It means that will give the electron here. Hydrogen. This red color electron is from hydrogen atom, you can consider like this. Okay, so finally what is the hybridization I told you? sp3, carbon is having sp3. So now 1s orbital here, other one will be like this, other one will be like this, and other one will be like this. So total 4. So what is the angle between them? 109.5 degrees. Okay, and each orbital will be overlapping with hydrogen atom like this. So 2 electrons here in each of the cases like this. Okay, so what is the angle I told you? 109.5 degrees or 109.28 minutes. 109 degrees 28 minutes you can write. Okay, is this clear up to here? Right. Now this is the orbital representation. If I want to represent in the normal bond line notation, you can also write it like this. This is a 2-dimensional representation, I mean normal line representation, but on a 2-dimensional paper I would like to represent in a 3-dimensional view. It means you should represent it like this: 1 hydrogen, second hydrogen, okay, and one more you should imagine like this. It means this thick line is there now here. This is representing, it is coming towards the observer. If this is the plane, the carbon hydrogen is coming out like this. Solid wedge, solid and wedge dash. This is dash line, wedge line you can say. Okay, this is a notation of that. So it is going below the plane. If this is the carbon we have, dash will goes below the plane, and that solid will comes above the plane, and these 2 normal lines will be within the plane. Now how many atoms are within the plane? 2. This one and also carbon, right? So 3 are within the plane and 1 is above the plane, other one is below the plane. What is the angle I told you?
109
degrees 28 minutes. You can remember it like this. Okay, right. Yeah. Is this clear? So what is the shape you can say? This is what? Tetrahedral. TD I am writing in the short form. Now just remember, so how these are something like, pyramidal shape, pyramid, how the pyramid will looks like. Yeah. Now what I am saying is, just remember like ammonia case I am going. This is about methane over tetrahedral. Now what I am saying, now just imagine I am catching this above hydrogen like this. Now how these 3 bonds will looks? Like a pyramid right now. So if we remove this, we are going to get a pyramid. And next one is, now if we remove this above 2 bonds, how it is looking? Like a V shape, like a V is coming here. Okay, so these are the scenarios when you have non-bonding electrons. What do we mean by this non-bonding electrons or lone pair electrons? Look at here, ammonia I am taking. Okay, so in this case also nitrogen have how many electrons? Like 1s2, 2s2, 2p, 3. So 5 valence electrons are there right now. 1, 2, 3, 4, 5 valence electrons are there. Okay, so now these will combine to give us 4 hybrid orbitals, same as sp3. Okay, so with 1 orbital already filled. But you need exact structure, no? That's what I am giving. So hydrogen here, here, and here we have. So now what we have here finally, total hybrid orbitals are 1 is s, remaining 3 sp3 we got. Okay, sp3 means again tetrahedral orientation you can have around the nitrogen atom. You can have something like this. Okay, so but in one of the orbital we have lone pair right now. So I am keeping it here, and the remaining other will be having 3 hydrogen atoms like this. Yeah, these are the bond pairs here. Okay, so now here nitrogen, hydrogen, hydrogen and hydrogen, or you can represent this as the above the plane solid and this is dash line, okay, and lone pair over here. See the bond angle previously in the methane molecule having sp3, what is the angle we found? 109.5 degrees, but here it is around 107. What is the angle I am saying? So why this angle is reduced here?
Because of the lone pair.
See, these lone pairs and bond pairs are there, 107 here. So just remember here why it is so. The reason also I will explain here. 107, because presence of lone pairs, what it is making, see the bonded electrons are, see here in these all the cases, in the bond case, in the bond formation, bonding electrons are shared between the two nucleus. Right now the two nucleus will drag them towards themselves, but in this case what happens, the electrons are sitting only on nitrogen atom, so therefore they have more repulsions whenever like charge come towards or near to them, therefore they will suffer with more repulsions. So in order to avoid that repulsions, to minimize the repulsions, the lone pairs will accommodate with maximum space and the bond pair will be comes closer, therefore bond angle will be reduced here.
So in VSEPR also it is mentioned lone pair repulsion.
That is what I am saying. So here due to the, here itself I combined that statements also I am giving here. So due to the lone pair bond pair repulsions, the bond angle is getting reduced. So in the valence shell electron pair repulsions we will be studying that lone pair repulsions are more than lone pair and a bond pair. When I compare this, then I have bond pair. So minimum is for bond pair. So therefore since they have minimum, they will go closer to avoid this lone pair bond pair repulsions. Okay, that's what bond becoming 107 degrees. Okay, and after this if we talk about water molecule, we have something like this with two lone pairs here like this. So now lone pair repulsions are more now. So what happens? They will pushes the sigma bonds closer. Therefore bond angle further decreases. It becomes around 104.5 degrees in water molecule. Okay, and what is the shape looking like? V shape or bent shape you can write. Okay, clear? Yeah. So let us move for valence shell electron pair repulsion theory in order to understand it more better way. Yeah, look at here. So we have valence shell electron pair repulsion theory. So according to this theory, the shape of a compound depends on number of type of type of electrons around the central atom. Okay, for example, around the central atom we have seen something like lone pair electrons and something like bond pair electrons. The electron pair present between two atoms are bond pair electrons right now. So we have type lone pair electrons and bond pair electrons. So in these lone pairs will be having more repulsions when I compare with the bond pairs. So lone pair repulsions are more than the bond pair or bond pair lone pair. Okay, this is the order you should remember first. Again we have something like sigma bond and a pi bond also. So now pi bond will be having more repulsion than the sigma bond. Okay, we will be solving them, we will be looking into this kind of examples. Okay, and see double bond give more repulsion than the single bond. It means whenever I have double bond and a single bond, so repulsions will be more in which case? Double bond. Okay, so when we solve questions you will be getting more clarity on this final last statement. Okay, as of now you write these two statements, we will do some questions so that get more clarity about this. Okay, so first of all tell me what is the order I given you? Bond pair is least. So what they are asking, correct, predict the correct one. So which one? So correct one is least, third one. Next, so which statement is correct in this, tell me? We have studied about methane and water and ammonia. Right now these three molecules are already done, remaining I will tell you now. So just tell me which is correct out of these four statements. HOH bond angle in water is smaller than NHN bond angle in ammonia. How much bond angle I told you here? 104.5. Here 107. Here 109.5. So as per this, this is correct only. They are saying false statement. Okay, that is correct statement. This one, the HCH bond angle in methane is larger than NHN bond angle in ammonia. This is also correct only. Next one, HCH bond angle in methane and the NHN bond angle in ammonia and HOH bond angle in water are all greater than 90 degrees. Okay, next one, HOH bond angle in H2O is larger than HCH bond angle in methane. Is this correct? No. HOH bond angle is minimum right now, which is having only 104.5. So fourth option is false one. That is the question you need to choose here, right? Yeah. Let us move forward with a few questions and explanation first. Yeah. Look at these. I have something like this. See, I have BeCl2. So what is the central atom here? Beryllium. So 2s2, 2p0. Beryllium atomic number. Okay, like 1s2, 2s2, 2p0 we are writing. So 2s2 means we have 2 electrons in this, but how many bond pairs are required? 2 atoms are there means 2 surrounding atoms there means 2 bonds are required right now. So it means this electron will be jumps here and will be having like this right now. So here one chlorine, here one chlorine. So what is the hybridization we are getting here? sp. So sp hybridization means s and p orbitals are mixed to get sp. So those 2 orbitals should be adjusted in the 3-dimensional space with minimum repulsions. In order to put minimum to have minimum repulsions, what is the best way to arrange them? With the maximum separation. So what is the maximum separation we can do? Like this, 180 degrees, something like this. So this is what the structure you are going to get. Beryllium at the center and one boron, one chlorine here, other chlorine here. So what is the angle you are getting here? 180 degrees. That's it. Okay. Next case is BCl3 is an example for what is the hybridization we got in the previous case? sp. Here it is sp2. Okay. So in sp2 how many orbitals are involved? 3. So now you need to arrange 3 orbitals in the 3-dimensional space with minimum angle. With maximum angle, minimum like yeah, it will become a 2-dimensional because only 3 are there now. But you just imagine in the space of sphere, you are just arranging that. Okay. So what is the best way? So keeping them with 120 degrees right now. So your angle will be 120 degrees. So yeah. So here 360 by 3 you can see. So here BCl3, BF3, this kind of molecules you can take. So now I will tell you one simple trick to do all the time. So what is the central atom here? Boron now, atomic number 5. Valence electrons are 3. So take 3 dots. Valence electrons are 3. How many surrounding atoms are there? 3 are there. They are also monovalent. It means they make only one bond each. Okay. So this will be one bond and this one and this one. Okay. Totally how many sigma bonds we got? 3 sigma bonds. So 3 sigma bonds means one is S, P are 2. So total sp2 hybridization. That's it. Simple. Like this you should do. Okay. Next. So what is the name of this hybridization? This shape geometry? Triangle like is there, it is like triangle. So trigonal planar. In a plane it is with a triangular shape. So trigonal planar with 120 degrees. Okay. Next one is what? We have methane. Okay. Methane we already discussed now. This is the structure of methane. I mean for sp3 hybridization. Okay. Yeah. This is the best example for standard example for sp3 hybridization. So in this case 109.5 degrees already we discussed. And what about this one? Ammonia case we discussed now. So it means this is sp3 hybridization with 0 lone pair electrons. this is also sp3 hybridization with one lone pair electron. And water case, this one is what? This one is what? This is also sp3 hybridization with two lone pairs. We already discussed these three things. Okay, with their bond angles, everything is discussed. Okay, right. Next one is what? We have something like PCl5. Okay, so what is the hybridization we will get? 3 over sp3d. Okay, so this sp3d case, what is the central atom here? Phosphorus. So put 5 electrons here like this. Okay, how many surrounding atoms? Like this, 5 chlorines are there. So you got how many sigma bonds? 5 sigma bonds. So you can say sp3 5 now, s1 p, p's are 3. So sp3 means 4 over, next one should be d orbital. So sp3 d. Okay, now in this sp3 d hybridization, which d orbital is involving? That is the question, because we have like dxy, dyz, dxz, dx square y square and dz square. So out of these 5, so here orbital involved is dz square orbital. What is that? Dz square. So with this hybridization, we are going to get trigonal bipyramidal geometry, TBP in the short form. It means trigonal, it means triangle. Bipyramidal, it means 2 pyramids on this triangle, you can remember like that. So something like see, I am writing it, see what is the central atom here? Phosphorus, right? So one bond here, other bond here, other bond here. Okay, so just join them. How it is looking? Like this, no? Triangular shape. So what is the angle in this case? 120. Okay, so what is the angle here also here? That is also 120. So now I am writing the pyramid now. See, 5 bonds are required, only 3 are represented here. So this is the best way you can place them like this. So what is the angle here you are going to get? 90 degrees. So these green color lines are called axial lines. What is that? Okay, and these white color lines are called equatorial lines. Okay, so if you look at these, this is the orbital representation. Okay, right. So just draw it. Just draw it. Over up to here. So what is the angle? We have two types of angles, one is 120, other one is 90. Now here PCl5, like trigonal bipyramidal, is one of the very important structure that to be studied very clearly with complete diagnostic. Okay, so look at here, like how it is looking, like a trigonal here, triangle with one above pyramid, like above line and below line. So now if I join these above lines, just see, if I join this white lines with this above one, we are going to get a pyramid, above one pyramid as well as below also we are going to get a pyramid. So trigonal bipyramidal, you can remember. So how many types of angles are there? 2, 120 and 90. Okay, so how many 120s are there? 3 120. See, this is 1 120s, 2 3. This kind of questions also you can see. And how many 90s are there?
2. 180 degree also possible.
180 is possible. See what I am asking here, how many 90s are there? That is what the mistake here students will do. See, if this is central atom, 1 2 3 are there like this now. So above line, below line. So just count now. See, with these we can have 190 here, and with these we can have second 90, and this is 390 is above, similarly 390 is below. So total 690s are there. 690 degrees are there. How many 120s? 3 120s are there. Okay, this type of questions also you can expect. Okay, right. And next one is we are studying about PCl5 right now. So now PCl5 means sp3 hybridization. How many lone pairs? 0 lone pairs on central atom. On central atom 0 lone pairs. Now I am saying sp3. What is the next possibility? sp3 hybridization with 1 lone pair. The example here I can give you is SCl4. The best example here we have. Okay. So what is the sulfur group number? Fast. What is the sulfur group number? Sulfur atom belongs to 16th group now. So 16th group. So it has 6 valency electrons. So put 6 dots like this. That 6 valency electrons. Okay. And how many surrounding atoms are there? 4. So 1 chlorine, second, third, fourth, and remaining one will be remains as lone pair. So how many sigma bonds and pi bonds are there? 4 sigma bonds and 1 pi bonds, don't consider. How many sigma bonds are there? 4 sigma bonds, 1 lone pair. So always for hybridization number, you just take number of sigma bonds and lone pair electrons, not pi electrons.
sp3 only. 4 sigma bonds, so sp3 only.
Yeah, what I am saying, for calculating hybridization number, take count number of sigma bonds plus lone pairs.
So the lone pair is not participating in the bond.
It is not participating in the bond, but it will affect on the bond angle. Okay. So for example, ammonia case, what you did? You got something like this now. Like this, you have one hydrogen atom here and the other one here, other one here. So total hybrid, what is the total hybridization you got?
3.
sp3. This one and all these 3 are involving sp3. Similar to that, here also 4 sigma bonds and 1 lone pair. So total hybridization is how much now? 4 plus 1, 5 now. It means 5 means sp3d with 1 lone pair. Okay. So now the structure will be, see, out of these 4 bonds, out of these 5 bonds, one of the position is occupied by, see, surrounding atoms are 4 only. It means the one of the 5th position should occupied by lone pair. But what is the position we need to take here? That is a question.
But the angles will also change.
120, 90.
Yes, but here that was for bonding electrons. Lone pair has more repulsion.
That's what. Once if we got the structure, then we will discuss about that. So now the question is where to place this lone pair, either in this green color line or white color line. That is the question. So very simple. Where do we have minimum repulsions? Lone pairs will suffer more repulsions, we know that. Okay. If you place them with a maximum separation, then they will be having minimum repulsion. So where do we need to place? See, here we have 90 degrees. Here we have 120 degrees. Where is the maximum angle separation? So lone pair should be kept in the, these white lines are equatorial, man. These are called axial. See, XYZ means how you will write like this now. Along the axis you have this line now, so you just remember like that. Okay. So along the axis will be having 90 degrees only, but equatorial lines are having 120. So what is the best position to keep that lone pairs? Equatorial. So now we have 3 equatorial positions. Any one of that position you place this lone pair first. So central atom you write first, central atom, and 1 orbital, second and third, here we have something like this, and axial bonds here and here. So but what I told you, one position first give the place for lone pairs. So this is a position I am giving it for lone pairs. Remaining other positions are occupied by the surrounding atoms. How many are there surrounding atoms? 4 are there now. So chlorine here, here, here and here. This is how you will get right now. So now what about this shape or the name of this shape. So this is called seesaw. What is the name? This is called seesaw shape. What is that? Seesaw. Okay, so look at here, something like, see, so here you have one axial bond, here one axial. Equatorial position is occupied by lone pair. So now you know even these axial bonds also will be bent this side. Why? Because lone pairs will have more repulsions. Okay, so seesaw shape you can say. Other ways, how many bonds are there here? 4 bonds are there. Huh? So you can also say 4 bonds. We are saying if 4 bonds are there means tetrahedral shape we will say. But due to the presence of lone pairs, they will angle is changing here, the 5th bond. Okay, so you can say this is distorted tetrahedral. What is that? Distorted tetrahedral. Okay, these are the 2 names you should remember. Okay, I will ask you later. Okay, and after this I will give you one more example. Take ClF3 I am taking. So ClF3, tell me for this case, what is the central atom here? Chlorine. So how many valence electrons are there with the halogen chlorine here? 17th group now, 7 valence electrons will be there. Okay, so put that 7 dots here. Okay, so how many over? 3, 3, 6, 7 over. Okay, how many surrounding atoms are there? 3. 1, 2, 3. So after these 3 sigma bonds, you have one set of lone pair, the other set of lone pair. So it means how many sigma bonds? 3. Sigma plus 2 lone pair. So total number is 5. 5 means what is the hybridization? sp3d with how many lone pairs? 2 lone pairs. Okay, you can write it like this. Now tell me what I can do, what is the geometry we will get? Like electronic geometry will be, you are saying trigonal bipyramidal will be the electronic geometry. But the molecular geometry, if I ask, what is the molecular geometry will say? Like arrange this sigma bonds and lone pairs. How can we arrange? Tell me. Central atom is chlorine. Now this will be the structure if we properly write it. Like this. But you know how many lone pairs are there? Only 3 sigma bonds will be formed, remaining are lone pair. Where do we need to keep that lone pair? On this red color lines or green color lines? Equatorial position now, so green. So you can take here and put one lone pair here. This is one set of lone pairs, and this one also remove and place one more lone pair here. So how the shape is looking now? One fluorine here, the other fluorine here, and the other one is here. Something like you have a T shape, see, like a T, like this. So what is the shape of this? When you have sp3d hybridization with 2 lone pairs, you will be having a T shape. Okay, write it. Okay. Next, shall we move forward? Yeah. So next I will be giving you one more example, and with this one example I will be stopping here. I am giving you few questions. Okay, you can do it at your home. So take this ICl2 minus. So how many valence electrons are there here? Halogen element, like what is the central atom here? Iodine. How many valence electrons are there with the iodine? Halogen na 17th group. So 7 valence electrons will be there. Okay, so how many over? 6 over 7 valence electrons are done here. And what is the charge you are seeing, overall charge on this? Minus. So it means you need to add one more electron. If you have plus charge, remove one electron. Minus charge, add one electron. If it is minus 2, add 2 electrons. If it have plus 2, remove 2 electrons. Okay, so chlorines are how many are there here? 2. So one chlorine here, the other one here. Okay, and this is one set, other set, and the third set. So it means how many sigma bonds or how many pi bond, how many lone pairs? 2 sigma bonds plus 3 lone pairs. So total number is 5. So 5 means? Tell me first. Tell me here. SP 3 sp3d, sp3d with 3 lone pairs. So now in the trigonal bipyramidal geometry, you have how many lone pairs? 3 lone pairs. So what about the structure now? How it will be impacted? How it will be changes? See?
Linear.
Yeah. So like iodine here. So this one like this. We have above one, below one. How many lone pairs are there? 3. Where do I need to place these 3 lone pairs?
On the equatorial.
Equatorial. Because maximum separation.
Yes. More angle.
Yeah, more angle. So bonds are only 2. So chlorine above one chlorine, below one chlorine. How it is looking? Like a line now, linear I can say.
Nice.
So what is the angle here? 180 degrees. Okay, and you can say this is linear. Molecular geometry or shape is linear. Okay, clear now? This one also? Right. Okay, let me check any questions are there with these, or else I will give on my own. So try this question. Okay, and along with these I will check your notes on the next class and try these questions also. I will be checking these. Okay, and along with that let me check once more. I will explain everything, but once you give a try. And these questions also, all these are PYQs either of NEET, JEE or EAPCET. Okay, and these questions also, all these questions are must be solved. Okay, right. So these are enough. If you solve these questions, yeah, sufficient, and you can go through the other questions from our modules. Okay, and if you have any doubts, you can ask me. If you have any doubts now, you can ask me now, or else we'll wind up the class. Yeah. So those who are in the online live session, those who have watched this, so if you like the session, please click on the like button, and if you are new to this channel, just click on the subscribe button also. Thank you.